Hey, welcome. Have you ever stopped to think about how your phone can find a single photo out of thousands in just a blink? Or how your music app can instantly shuffle a playlist of 10,000 songs? Well, a huge piece of that magic comes down to one really fundamental idea: sorting. Today, we're going to pull back the curtain on the elegant logic that brings order to our crazy digital world.
But let's start bigger. Think about it. We humans are wired to create order out of chaos. We make lists. We put things in categories. We arrange stuff. It's just how we make sense of everything. And it turns out computers are facing the exact same problem, just with mountains and mountains of data.
So to get a handle on this whole order from chaos thing, we need to know exactly what we're talking about. What does it really mean to take a completely jumbled mess of information and turn it into something that's actually coherent and useful?
At its absolute core, the idea is super simple. Sorting is just arranging items in some kind of sequence, like A to Z or smallest to largest. Sounds pretty easy, right? Well, the how, that's where things get really, really cool.
To get our heads around this, we're not going to start with a bunch of complicated code. Instead, let's look at a method so natural, you've probably done it 1,000 times without ever thinking, hey, I'm running an algorithm right now.
Just imagine you're sitting down for a card game. You get dealt your hand. You don't just leave the cards all jumbled up, right? Of course not. You pick them up one by one and build a sorted hand as you go. And that right there, that's the perfect way to think about our first algorithm, which is called Insertion Sort.
So check this out. Let's say you're already holding a 6, a 10, a 24, and a 36, all nice and sorted. Then you pick up a 12. What do? You instinctively find its proper spot, right between the 10 and the 24. And you kind of shift the bigger cards over to make room. Just like that, your hand is perfectly sorted again.
Okay, so let's put that into actual steps. The algorithm grabs the second item in a list. It looks at the one to its left and asks, hey, am I smaller than you? If the answer is yes, it swaps. And it keeps doing that, shuffling its way to the left until it finds its correct home. Then it just moves on to the next item and does the whole thing all over again, slowly building up this sorted section of the list.
And Insertion Sort is awesome. It's super easy to get your head around, it's pretty quick if your list is already mostly sorted, and for small jobs, it's fantastic. But you probably noticed that little asterisk at the end there, for small lists. What happens when we try to go big?
And that brings us to the giant brick wall our simple, intuitive little method is about to slam into. The logic is fine. It's beautiful even. The problem is the sheer, mind-boggling scale of data in our world today.
So let's say you're not sorting 10 cards anymore. You're sorting 100 million items. Maybe it's 100 million users for a website, or 100 million financial transactions. All of a sudden, that one-by-one method feels painfully, impossibly slow.
This is where we have to talk about something called complexity. For Insertion Sort, its performance is described as O of n squared, or big O of n squared. Now don't let the jargon freak you out. All it really means is that as your list gets bigger, the amount of work the computer has to do grows way, way faster. If you double the number of items, you don't just double the work, you quadruple it. Triple the items, you're looking at 9 times the work. You can see how this gets out of hand really fast.
I mean, let's put some real numbers on that. For 10 items, it might take, say, 100 little operations. No biggie. But for just 1,000 items, we're suddenly at 1,000,000 operations. We've fallen right into the n-squared trap, and it's not a place you want to be.
So that begs the really important question. If the simple, human way of doing things completely breaks down its scale, how in the world do we handle the massive data sets that power everything we do? We're going to need a completely different approach.
And that smarter approach has a really cool name: divide and conquer. Instead of trying to wrestle with this huge, messy list all at once, we're going to be way cleverer. We're going to break it down into tiny, easy-to-manage pieces, solve those little puzzles, and then put it all back together.
This brings us to a really powerful algorithm called MergeSort. And the logic is actually beautiful. You just split the list in half. Then you split those halves in half. You just keep splitting again and again until you're left with a whole bunch of tiny little lists that only have one item in them. And here's the genius part. A list with only one item in it is already sorted, right? By definition.
This is what that divide phase looks like. You take your big unsorted list and you just keep chopping it. One list becomes 2, then 4, then 8, all the way down until every single number is just sitting there in its own little box. You've basically broken the chaos down into its smallest possible parts.
And now for the conquer phase. This is where the magic really happens. We start merging those single item lists back together,
So we take two sorted lists, like one with just a 27 and another with a 38, and we merge them into a new, bigger, sorted list, 27, 38. And we just keep doing that, merging 2-item lists into 4-item lists, 4 into 8, and so on until it all comes back together into one final, perfectly ordered list. It's so elegant.
And the result of all this cleverness is an efficiency of O of n log n. Again, you don't have to be a math genius here. Just know that this grows so much slower than O of n squared. We're talking about the difference between sorting a billion things in a few minutes versus, well, maybe a few years. It's a total game changer.
So, is MergeSort the best? Is it the one algorithm to rule them all? Well, not so fast. This brings us to one of the most important lessons in all of computer science. It is always about trade-offs. There's almost never one single best answer for every single problem.
Just take a look at this. MergeSort is a rock star. It's predictable, always giving that great O of n log n performance. But check out Insertion Sort's best case. O of n means it's blazing fast if the list is already pretty much sorted. And then there's another famous one, QuickSort. It's usually faster than MergeSort in the real world, but it has this tiny chance of having a worst-case day where it's just as slow as our simple insertion sort.
So here's the big takeaway. Choosing the right algorithm is all about knowing what your job is. Are you sorting the top 10 high scores in a simple phone game? Insertion Sort is perfect. It's simple and it's more than fast enough. Are you sorting a gigantic database for a bank where consistency is absolutely critical? MergeSort is your best friend. It's all about picking the right tool for the job.
And that kind of leaves us with one last big thought. We've only just scratched the surface of how computers create order out of digital chaos. And if this much thought goes into just sorting a list, it really makes you wonder, right? What other incredible, invisible algorithms are humming away in the background, shaping our world in ways we don't even see?